All right. In this video, we're going to take a look at 3 paper airplane designs. So paper airplane design number 1, design 2, and design 3. And so you can imagine building paper airplanes and trying a different design and then throwing it and measuring how far they go. And so if we look at the first design here, 1 airplane went 9 feet, 2 airplanes went 10, 3 went 11, 2 went 13, 1 went 15, and 1 went 17. Fantastic. And so when we find the mean of those, we get 12 feet. Airplane design 2 was 12.9, airplane 3 had 14. And so just on the surface, we might say, well, airplane 3 looks like it's the best because it has the highest mean. Okay, but we're going to take a look at measuring variation using the mean absolute deviation, sometimes abbreviated MAD. It's definitely higher. This is about 1 foot further. This is about another foot further. So it seems like we're pretty confident in this. But this measure of variation is going to give us something to think about. So let's go ahead and calculate the mean absolute deviation. So to get started, we first have to review MAD, what it means. If you remember, I said it's the average distance values are from the mean. So in this first example, they've already found distances from the mean. So how far is 9 from 12? Well, it's 3. Now, probably just almost intuitive to look at it and say it's 3 away. But what if you were using a decimal or there's a bigger spread? Or what are you actually doing mathematically here? Mathematically, you're really taking 12 minus 9 to get 3. Okay. And then how far is 10 from the mean, which is 12? Remember, the mean's 12. Well, that's easy. It's 2, right? But again, it's just 12 minus 2. Here, 12 minus 11. Now I get to 13. I want to throw in why they call it mean absolute deviation. If you did the subtraction here of 12 minus 13, you would get -1. If you put absolute value bars in, now it becomes a +1. And so we are interested in the absolute deviation. How far is it from the mean? Not making it positive or negative one way or another. So that's why it's called mean absolute deviation. So 13 is 1 away from 12. 15 minus 12 is 3. 17 minus 12 is 5. So these are all the distances that these numbers are from the mean. Now, how do we find the average distance? Well, just like we would any other average, we would add these all up and divide how many there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 items, 10 airplane trials. So I need to add these all up. The sum turns out to be 20. So the mean absolute deviation then is 20 divided by 10, which is 2. So that means the average distance that these planes are from the mean is 2. And we can kind of see that. They range roughly from 14 down to 10. Now, not exactly. We've got a few further away, but on average, 14 to 10 catches it pretty closely. All right, let's do this same thing for mean for airplane design 2. We've got 12.9. First thing to find the MAD, or the mean absolute deviation, we have to find how far is each from the mean. So here's where our subtraction might be a little more useful. We've got 12.9 minus 11. That's going to give me 1.9 away. And then I take the next value, 12.9 minus 12. That's 0.9 away. 13, I'm just going to switch it around. You could do absolute value bars if you wanted to, but I don't think most people want to. So we're going to get 0.1 3 times. 14 minus 12.9 is going to give me 1.1. And 15 is going to give me 2.1. When I take the sum of these numbers, I get 9.2. And so the MAD then, since there's 10 values, the mean absolute value mean absolute deviation will be 9.2 divided by 10. We get a mean absolute deviation of 0.92. Repeat the process here. The mean is 14, so 12 is 2 from the mean. 13 is 1. 14 is 0 from 14. 15 is 1 from the mean. And 16 is 2 from the mean. So if we now find the sum of those numbers, we get 10. Again, there's 10 values. So the average distance will be 10 divided by 10, which is 1. So we get a mean absolute deviation of 1. All right. So I think the next page or the next questions are going to ask us to use the means and the MADs from part 1 to discuss how the three paper airplanes compare. So how do they compare? Pause the video and just think about it for yourself a second. How do they compare? Well, just on a kind of simple level, we could say, well, this mean is the highest, then this one, then this one. This has the most variation. It's the highest MAD. It's spread out the most. And then these two are about the same in variation. And we also see that in the picture. The variation here is between 11 and 15 for a range. It's fairly tight. Here, 12 to 16, but again, fairly tight. So we see that's similar. Here, though, we see it's more spread out, which is reflected in the MAD. It's bigger. Let's take a look. The rest of the question. How confident can you be in saying that one airplane flies farther than another? Well, it kind of depends here. If we just took a random airplane from design 1 and a random airplane from design 13, from the mean, we would say that this one is bigger. It'll do better. But if you'll notice, if you look at, there were 2 airplanes that got 15 or 17. Okay, so 2. But there was 4 that got 15 or higher on this design. So even though quite a few of these were below, we did have some that flew. We did have some here that flew better than these, right? But this does tell us it's more spread out. So can we confidently say this one is better than this one? Pretty close. I mean, we had some. How is that reflected in the mean and the MAD? So here, if you look at the mean, it's 14. If we go 1 below, that would be 13. We're still quite a bit, I say quite a bit, we're still above this mean. But if we look here, that's not quite as far. If we would go 1 below here, that's 13. That almost catches the average, and we see that here, don't we? Again, this is spread out 0.92. There's a lot of overlap here. You can see these all overlap. And so we have to be careful by just looking at the mean and saying, oh, this means better, it's the best. Well, it does appear that the center is higher than here. But there are also some airplanes here that are below the center here. And so we really have to take into account and say, you know what, these aren't that far apart. We might have just got some really good throws here, or maybe there was some sort of breeze or something helping us here. And so the mean absolute deviation is able to kind of show us that these numbers are spread out. If I go 1 below 14, that's 13. Go 1 above this, that's 13.9. They're really not that much different. So I would say we can't be very confident. Slightly, seems like it, but we probably should get more data. Question 3 says, suppose there's a 4th paper plane for which the mean is 13.9 and the MAD, or the mean absolute deviation, is 1.1. Discuss how this 4th airplane compares with 2 and 3. Okay, so airplane number 4, mean and MAD. Was this 13.9, I think, and 1.1. I feel like this one is very comparable to airplane 3. We see the means are almost identical and the MADs are almost identical. So again, probably lump it together. Maybe a little bit better than airplane design 2, but not every airplane, and we can't be confident that the difference is due to the design. It might be just other variation that's happening, other factors. So with that, I'll do a quick review on calculating mean absolute deviation and the meaning. So calculations, we just have to find the distances from the mean. Once we find those different distances, we find the average distance. So we have to total these 20. Here it's 20, and then there's 10 points. So we take 20 divided by the number there is, 10, to get 2. And so that means we have a mean of 12. We can expect numbers to range from about 10 to 14. Here we can expect them to range from about 12 to 13. And here we can expect them to range from about 13 to 15. Smaller MADs means the data is closer together. Larger mean absolute deviation means it's more spread out. And that's really the key point to this video.